Hey there, scientists. So today we're talking about work and energy and how they are related. So looking at previous big ideas, we looked at how work is measurement of force and distance. So we write it work, or W equals FD. Those units for force are in newtons and for distance, meters. So we have a unit of Newton meter. So capital N, little m, it can also equal 1 joule. Right? So those are both the same type of unit. We also saw that with this ramp or any type of simple machine, it doesn't necessarily reduce or it doesn't reduce the amount of work done. There's a trade-off, and there's a trade-off between force and distance. So pushing this block up a ramp actually takes less force than lifting it straight up into the air, all right? However, there's more distance, so there's trade-offs. So in a simple machine, you have less force, but you have more distance, right? So the work done is still the same. So anytime you're moving a force over a distance, you are doing work. Now, not all work is completed or equally, right? So sometimes you complete work in a faster amount of time. So work divided by the amount of time you take in seconds is power. So this new unit is joules per second or a watt. So typically we're going to be seeing work measured in Newton meters more often and energy measured in joules, but they are the same thing. Okay. So what is energy? Well, in order to do work, you need energy. So the ability to do work, your force times distance, comes from energy. There are many different forms of energy, but it's still going to be measured in Newton meters or joules. Again, you're typically going to find energy measured in joules more often, okay? Energy equals the amount of work done. And we're going to see a couple of examples of how those formula, you just rearrange that formula to get your energy formula. So it can change different types. I could have chemical energy, thermal energy, nuclear energy. The energies that we are going to focus mostly on are potential energy, specifically gravitational potential energy, and kinetic energy. Okay. So potential energy, starting off with that gravitational potential energy, is just stored up energy. So if I take this tennis ball and I move it up a distance, I have now done work on it. Okay. I have given it potential energy. It has the potential to fall, right? So gravity pulls it down. So potential energy, the formula for this one is the mass of this tennis ball, and usually we measure mass in kilograms, times gravity. And if you recall from our earlier units too, gravity on Earth here, we're going to use 10 meters per second, okay? Since we're measuring gravitational potential energy, that is assumed that we know that that is down. And then height is going to be measured in meters, right? So we have mass times gravity times height. Now it looks like a brand new formula, but it actually isn't. If you recall back to when we found our weight. So weight is mass times the acceleration due to gravity. Well, really, that's that first part right there. So mass times gravity is your weight, that's force. Your height is just a vertical distance. So really, work is FD, it's the same as your potential energy that you are giving to the system. So mass times gravity times height. Work equals energy, okay? So when you look at the examples of different heights, this is how you increase your potential energy. So a greater height, more potential energy. The blue skier has a greater height above the surface, so he starts off with more energy than the red skier, okay? Another way to figure out more potential energy would be more mass. So the green skier here has 600 newtons of force, so that's his mg. So he has or she has more potential energy when they start at the same height than my yellow skier that has a smaller mass and a smaller than mg weight, okay? We find potential energy. So for this skier, imagine that this skier has a mass of 50 kilograms and they're standing on a slope that is 15 meters high. What is the potential energy? So remember, you start off writing your formula, PE equals mgh. Plug in the numbers, so 50 kilograms times 10 meters per second times 15 meters. and we get then a potential energy of 75 joules. Now, again, you could say 75 Newton meters. Typically, we use joules when we describe energy. Right? So if I have that amount of energy at the top of the hill, the skier then skis to the bottom of the hill. So what happens to the energy when she goes down the hill? Well, it changes forms and it starts to change into moving energy or kinetic energy. So energy of motion is kinetic energy. Now, a big idea we're going to come back to is that the total amount of energy is always going to stay the same. So we're going to change from, potential energy to kinetic energy. All right. So if I have 7,500 joules at the top of potential energy, at the bottom of the hill, all of that has changed to kinetic energy. And we will come back to that idea. So when we look at the potential energy, think about a car going down a hill. So for this particular example, I have a Hot Wheels car that they have caused it to enlarge here. And when we go down the hill, the potential energy decreases and it changes to kinetic energy. And then they use that energy to go up this little ramp and make the jump. And then some of that energy starts to transfer to more of a thermal energy from friction from the brakes. And of course, the sand that they land in, okay? All right, so it changes back and forth, right? So kinetic energy is the energy of motion. So it depends on both the mass and the velocity. And so this is our new formula for this one. Kinetic energy equals 1/2 mv squared. So mass times velocity squared. So 1/2 mass times velocity squared. Okay. So here, when we look at this mass is doubled, you're going to look at more kinetic energy. So the more mass, the more kinetic energy you have. However, a tricky thing is too, if you increase the velocity, that actually quadruples the kinetic energy because of that square. So watch the square when you're doing a problem. Okay. So finding a sample problem with kinetic energy equals 1/2 mv squared. Imagine I have a 625 kilogram roller coaster moving at 18.6 meters per second at the bottom of the hill. What's the kinetic energy? Okay, so again, plugging in your numbers, we're going to take 0.5, that's how I would enter it in the calculator, times 625 kilograms times 18.6 meters per second, and square just the velocity. You should get then a unit of 108,112.5 joules. Notice a joule is also the same as a kilogram meter squared over second squared, which is why we use that simpler unit of a joule. Okay. So today your mission is to start on this work and energy problem set. So solutions will be posted to Canvas, and then double check that you have submitted all 3 assignments from this unit. As always, please reach out if you have any questions, comments, concerns. Have a great day.